3 minutes ago, in the scale of everything the universe has ever done, is nothing. But 3 minutes ago, in the scale of a human news cycle, is everything. And right now, in laboratories scattered across Germany, the United States, and beyond, scientists are still opening files that were recorded by a machine that has been dead for nearly 9 years. A machine that burned up in the atmosphere of Saturn on September 15th, 2017. And what they are finding inside those files is not old news. It is some of the most electrifying science of this entire decade. Because Cassini's final images and the final measurements that came with them were never fully read. Not really, not until now. Stay with me, because what this dead spacecraft just told us is going to change how you think about our solar system, and maybe about our own existence. Let's go back to the beginning to understand exactly what we're dealing with. Cassini was not a small probe. It was not a quick flyby mission. It was, without exaggeration, the most ambitious robotic explorer NASA and the European Space Agency ever built together. It launched in October 1997, carrying the Huygens lander bolted to its side, and it spent nearly 7 years crossing empty space before it finally reached Saturn in 2004. From that point on, for 13 straight years, it orbited the ringed planet, weaving between its moons, diving through gaps in its rings, tasting its atmosphere, and photographing worlds that human eyes had only ever seen as blurry dots through a telescope. By the numbers, the mission is almost hard to comprehend. Over 400,000 images, 294 complete orbits of Saturn, nearly 5 billion miles traveled. It discovered vast seas of liquid methane on the moon Titan, the only other place in the solar system known to have stable liquid on its surface. It discovered towering geysers of water erupting from the south pole of a tiny ice moon called Enceladus. It mapped Saturn's magnetic field in detail no telescope on Earth could ever manage. And it flew directly through the ring system itself, close enough to smell what the rings were actually made of. But here's the part almost nobody outside of planetary science circles fully appreciates. When Cassini was designed back in the 1980s and 1990s, its instruments were built with the technology and the scientific assumptions of that era. The spacecraft could only send back so much data at a time, and scientists could only analyze it with the tools available at the moment. Which means an enormous amount of what Cassini recorded was essentially raw material, chemical fingerprints, magnetic readings, orbital wobbles, sitting untouched in an archive, waiting for a future generation of scientists with better instruments, better software, and a completely different understanding of what to even look for. That future is now, and it is rewriting the story of Saturn. Let's talk about the final days first, because they were genuinely one of the boldest things any space agency has ever attempted. By early 2017, Cassini was running critically low on fuel. NASA had a decision to make: let the spacecraft drift indefinitely, risking an eventual uncontrolled crash into Titan or Enceladus, both worlds now considered strong candidates for hosting life, and potentially contaminating them with Earth microbes still clinging to the hull, or take a different path entirely. They chose the harder option. They designed what came to be called the Grand Finale. For 22 weeks, Cassini was steered into a region of space that had never been explored by any human-made object before, the narrow 1,500-mile gap between the innermost edge of Saturn's rings and the top of its atmosphere. Nobody could say for certain what was in that gap. Some engineers worried the spacecraft might not survive even a single pass through it, that ring particles could shred its solar panels or antenna, but NASA sent it through anyway. Not once, but 22 times, instruments running full tilt, cameras open, sensors gulping in data from a slice of space that had simply never been sampled before. Then, on September 13th, 2017, just 2 days before the end, Cassini turned its cameras one final time toward the things that had defined its mission. Enceladus, Titan, the rings glowing gold in reflected sunlight, Saturn's northern hemisphere swirling with storms bigger than Earth. It sent those images home, and the world treated them exactly the way you'd expect, as a farewell, a goodbye photograph, beautiful, final, complete. Except they weren't complete at all. While the cameras were capturing those postcard images, the spacecraft's other instruments, the ones nobody was watching on the news that week, were recording something far stranger. Cassini's ion and neutral mass spectrometer, essentially a device that can identify the chemical fingerprint of whatever is floating around it, picked up something that stopped scientists cold when they finally sat down to fully process it. Complex organic material, carbon-based compounds, was raining down out of Saturn's rings directly into the planet's atmosphere, and at a rate far higher than anyone had modeled. Researchers had known for years about a phenomenon called ring rain, a slow trickle of charged particles falling from the rings toward the planet. But what? Those final grand finale passes measured was on an entirely different scale, material pouring into Saturn fast enough that if the rate holds steady, the rings could vanish entirely within the next few 100 million years. On a cosmic timescale, that is almost nothing. It means the rings of Saturn, arguably the most recognizable structure in the entire solar system, are not ancient, permanent fixtures. They are a temporary phase, a relatively short chapter in Saturn's 4.5 billion year life, and we happen to be alive during the narrow window when they exist at all. Then there's the magnetic field. This one keeps physicists up at night. Every planet with a strong magnetic field that we know of has one that is noticeably tilted relative to its spin axis. Earth's magnetic north is offset from geographic north by around 10 degrees. Jupiter's field is tilted. Neptune and Uranus are absurdly tilted, practically sideways. This tilt isn't a random quirk. It's actually required by the physics of how planetary magnetic fields are generated through churning motion in a planet's conductive interior, a process called a dynamo. A field with zero tilt shouldn't be able to sustain itself. Theoretically, it should collapse. Saturn's magnetic field is tilted by less than 1/10 of 1 degree. It is, for all practical purposes, perfectly aligned with the planet's rotation axis. And Cassini's final dives through that unexplored gap gave scientists their most precise measurement yet of just how strange this alignment really is. It shouldn't be possible, and yet there it sits. Some researchers think there's a hidden layer deep, inside Saturn, some kind of stable shell of helium rain or metallic hydrogen that's canceling out the tilt before it can show up at the surface. Others suspect our entire model of how planetary magnetic fields form needs to be reworked. Either way, Saturn is quietly telling us that something fundamental about planetary physics is missing from our understanding, and Cassini's last transmissions are the sharpest clue we have. And then, years after the mission ended, came the halo. In late 2025, a paper in the Planetary Science Journal pulled something out of the grand finale archive that had gone almost unnoticed for years. Saturn's rings, the thin, flat disk we all picture in our heads from 1,000 photographs, are not actually confined to that thin, flat plane at all. Cassini's cosmic dust analyzer, during those final close passes, detected a massive, essentially invisible halo of fine dust particles extending out to roughly 3 times Saturn's own radius above and below the ring plane. 3 times the width of the entire planet in dust that no telescope on Earth, no matter how powerful, had ever been able to resolve. It took a spacecraft physically flying through the material to even know it was there, and it took scientists until 2025 to properly untangle what those readings meant. The picture of Saturn most of us are carrying around in our heads, rings and planet, clean and simple, is incomplete. The real system is wrapped in a ghostly cloud of debris reaching far beyond anything ever photographed. As striking as all of that is, none of it compares to what happened with Enceladus. This is the discovery that actually stopped scientists in their tracks, the one being talked about as one of the most significant astrobiology results of the decade. Enceladus is small. You could fit it comfortably inside a country the size of the United States or roughly the length of the British Isles, with plenty of room to spare. It's an ice-covered moon, one of the brightest objects in the entire solar system because its surface reflects almost all the sunlight that hits it. When Cassini first arrived at Saturn, back in 2004, Enceladus was barely on anyone's radar. It was considered geologically boring, just another small icy rock. That assessment lasted less than a year. By 2005, Cassini had spotted something extraordinary. Enormous jets of water vapor and ice crystals erupting from long fractures near the moon's south pole, blasting material hundreds of kilometers into space, some of it escaping the moon's gravity entirely and feeding Saturn's faint outer E-ring. Those geysers told scientists something huge was hiding under the ice. A liquid water ocean, global, salty, kept from freezing solid by the constant gravitational flexing Saturn exerts on the little moon as it orbits every 33 hours. Over the following decade, Cassini repeatedly flew straight through those plumes, sampling what was inside. It found salts. It found silica grains of a very specific size, the kind that on Earth only forms when hot water reacts with rock at high temperatures, meaning somewhere on the floor of that hidden ocean. Hydrothermal vents were almost certainly active. It found simple organic molecules, too. Each discovery, on its own, was remarkable. But it's what happened when scientists went back to the data in 2025, armed with instruments and analytical techniques that simply did not exist when Cassini was still flying, that changed everything. In October 2025, a research team led by Nozer Khawaja at the Freie Universität Berlin and the University of Stuttgart, working alongside longtime Cassini scientist Frank Postberg, published a study in Nature Astronomy that drew a direct, undeniable line between the chemistry inside Enceladus and the chemistry that underpins life as we know it on Earth. The breakthrough came from a distinction nobody had been able to make cleanly before. Most of the earlier organic detections had come from ice grains that had been circulating for a long time out in Saturn's E-ring, grains that could be hundreds of years old, weathered and altered by cosmic radiation before Cassini ever sampled them. This time, the team focused on ice grains collected during one specific, extraordinarily fast flyby of Enceladus back in 2008, when Cassini blasted through the plume at nearly 18 kilometers per second, more than double the speed of earlier sampling passes, at just 13 miles above the moon's surface. That extra speed meant the grains hit the detector hard enough to fragment in new ways, revealing chemical signatures that had simply been invisible before. What came out of that reanalysis was stunning. The fresh plume material contained a whole new class of complex organic molecules that had never been identified in any of Cassini's earlier data. Aliphatic and heterocyclic esters and alkenes, ethers, and more tentatively, nitrogen and oxygen-bearing compounds. If those terms sound abstract, here's why they matter. Esters and ethers are basic components of lipids, the very molecules that form the membranes around every living cell on Earth, yours included. Their presence in Enceladus's plume doesn't prove life exists there. But it proves something almost as important, that the chemistry happening inside that hidden ocean is not simple, not static, and not ancient history. It is active, ongoing, and producing exactly the kind of molecular building blocks that, on our own planet, sit on the pathway toward biology. Frank Postberg put it about as plainly as a scientist can. These molecules found in the freshly ejected material prove that the complex organics Cassini detected in Saturn's E-ring are not just leftovers baked by long exposure to space radiation. They are readily available inside Enceladus's ocean right now. That single sentence flips the interpretation of a decade of prior data. It means whatever's happening under that ice shell isn't some frozen relic from billions of years ago. It's live chemistry, happening in the present, in a dark ocean nearly 1 billion miles from the sun. Lido. Author Nozer Khawaja was equally direct about the implications, noting that there are many plausible chemical pathways leading from what Cassini found toward compounds relevant to biology, which only strengthens the case that this small moon could genuinely be habitable. And notably, the team has said publicly there's still far more in the archived data left to explore. This single moon, barely bigger than the state of Arizona, may be running a more chemically rich, more biologically promising laboratory than almost anywhere else we've ever looked in this solar system, Earth excluded. And we only know this because a spacecraft that died in 2017 happened to fly close enough, fast enough, through the right plume at the right angle, back in 2008, to catch it. It's worth pausing here on the science of why hydrothermal activity matters so much, because it's the backbone of the whole Enceladus story. On Earth, at the bottom of our own oceans, there are places where seawater seeps down through cracks in the crust, gets superheated by contact with hot rock and magma, and comes bursting back up through vents, carrying dissolved minerals with it. These hydrothermal vent systems are not sterile. They are teeming with life, entire ecosystems of tube worms, shrimp, and microbial mats that have never seen a photon of sunlight in their existence. They don't run on photosynthesis. They run on chemosynthesis, organisms that extract energy directly from chemical reactions between hot vent fluid and cold ocean water. Many biologists consider these vent systems one of the leading candidates for where life on Earth actually began. If Enceladus has the same basic ingredients, warm water, dissolved minerals, and now a demonstrated ability to synthesize complex organic molecules, then the question of whether something similar could be happening under that ice shell stops being speculative fiction and becomes a serious, testable scientific hypothesis. That is precisely why Cassini's old data is generating new headlines nearly a decade after the spacecraft's death. Now, not every discovery pulled from Cassini's vault points in the same optimistic direction, and it's worth being upfront about that, because it makes the whole picture more credible, not less. Take Titan, Saturn's largest moon, bigger than the planet Mercury, wrapped in a thick orange nitrogen atmosphere and covered in lakes and seas of liquid methane and ethane. For years, the leading assumption was that Titan, like Enceladus, almost certainly hid a deep, extensive subsurface ocean of liquid water beneath its icy crust, kept warm by internal heat and tidal flexing. In September 2025, a fresh reanalysis of older Cassini gravity and rotation data challenged that comfortable assumption directly. The updated modeling suggested Titan's interior may not behave the way scientists had assumed, and that a large, deep, actively circulating water ocean may not actually be sitting under that ice after all, at least not in the form long imagined. It's a reminder that Cassini's afterlife isn't just about validating our hopes, it's also about correcting our mistakes, sending us back to the drawing board on assumptions that had been treated as settled for the better part of 2 decades. Then there's Mimas, and this one might be the strangest turn of all. If you've seen a photograph of Mimas, you already know it looks almost like a prop from a science fiction movie. A small cratered moon dominated by one giant impact crater that makes it resemble a certain fictional space station a bit too closely for comfort. For most of Cassini's mission, Mimas was written off as one of the most geologically dead objects anywhere in the Saturn system. No geysers, no detectable internal heat, just an old, frozen, cratered ball of ice that had probably looked exactly the same for billions of years. In February 2024, a team of scientists studying the subtle wobbles in Mimas' orbit, tiny variations in its motion around Saturn that Cassini had tracked for years, announced something nobody expected. Mimas has a liquid water ocean hiding beneath its surface too, and not an ancient one. Based on the orbital dynamics, this ocean appears to have formed somewhere between 5 and 25 million years ago, which, on the timescale of a 4.5 billion-year-old solar system, is essentially newborn. There is nothing about the outside of Mimas, no cracks, no plumes, no visible sign whatsoever that would tip you off. The only reason we know is because Cassini spent years quietly logging the moon's orbital wobble, data that sat mostly unremarked upon, until researchers finally ran it through the right models, years after the spacecraft had already been vaporized in Saturn's atmosphere. That is the pattern that keeps repeating with Cassini's legacy. Fly past something, record it, archive it, move on to the next target. Years later, with sharper tools and a better understanding of what questions to even ask, go back and find something that was sitting there the entire time, completely invisible until someone knew to look. Step back now and look at the full shape of what this one spacecraft actually handed us. A ring system that is actively dissolving into its host planet at a rate that gives it a genuine, measurable expiration date. A magnetic field so precisely aligned with Saturn's spin axis that it seems to break the physics we thought governed planetary interiors. An invisible halo of dust stretching 3 planetary radii beyond the rings anyone has ever photographed. A small ocean moon, Enceladus, spraying complex organic molecules into space that mirror the chemical building blocks of life on Earth, apparently manufactured continuously by an active, possibly hydrothermal ocean floor. Another small moon, Mimas, hiding a brand new ocean behind a completely deceptive, ancient-looking exterior, and a reminder from Titan that not every assumption survives contact with better data. All of that from one mission. One spacecraft. 13 years orbiting Saturn, capped off by 22 suicidal dives through a region of space nobody had ever dared enter before, and a final controlled plunge into the planet's atmosphere that destroyed the machine but did not, in any meaningful sense, end its work. Because here's the number that puts this whole story in perspective. Saturn is roughly 900 million miles from Earth, at the kind of distance Cassini was transmitting from during its final hours. Radio signals travel at the speed of light, but even light takes time to cross that gulf. Cassini's very last signal, the final proof that the spacecraft had done exactly what mission controllers designed it to do, reached the deep space network dishes on Earth at 7:55 in the morning, Pacific time, on September 15th, 2017. By that point, the spacecraft itself had already been gone for 83 minutes, torn apart and vaporized in Saturn's upper atmosphere. For 83 minutes, a dead machine kept speaking to a planet that had no idea it was already gone. And in a strange way, that hasn't really stopped. Every fresh paper pulled from the archive, every reanalysis run through instruments and software that didn't exist when Cassini launched in 1997, is Cassini speaking again, years, sometimes almost a decade, after its own destruction. Scientists working on the mission's archive have said openly that they expect the full scientific value of everything Cassini recorded to take another decade or more to fully extract. Every year brings new papers. Every new paper seems to bring another surprise nobody was expecting. None of this was really what Cassini was built to find either, and that might be the most important part of the whole story. Cassini wasn't launched with instructions to go hunt for the ingredients of life. Its instruments were designed to measure magnetic fields, map ring structures, characterize atmospheres, and study orbital dynamics, the unglamorous bread and butter of planetary science. It was a generalist explorer, sent to a system we barely understood, carrying tools built to answer the questions scientists in the 1990s thought to ask. And yet, buried in its final orbits, in measurements taken during a deliberate death spiral through unexplored territory, it captured evidence of molecules that build cell membranes. It captured the fingerprint of hidden oceans, inside moons that looked, on the surface, completely dead. It captured rings evaporating into their planet, at a rate that gives them a genuine countdown clock. It captured a magnetic field that, by the rules we thought we understood, simply should not exist in the form it does. None of that was on the mission's original checklist. It was all just sitting quietly in the data, waiting for the right combination of curiosity, patience, and better technology to come along and notice. This is really what makes the Enceladus finding land so hard when you actually sit with it. For those specific molecules, the esters, the ethers, the tentative nitrogen and oxygen compounds, to be present in the concentrations and variety Cassini's instruments picked up. The ocean producing them can't be some inert, static pool of salty water sitting quietly under the ice. It has to be chemically active. It almost certainly needs an ongoing energy source, and the leading candidate, backed up by those earlier silica grain detections, is hydrothermal circulation. Hot water meeting rock somewhere on that ocean floor and driving continuous chemical reactions. That is not a description of a dead, frozen world. That is a description of a world doing chemistry right now in the dark, under 60 plus miles from Saturn's warm embrace, in an environment eerily similar to the vent systems on our own ocean floor, where many scientists suspect life on Earth got its very first foothold. The space agencies have noticed, and they're not waiting quietly. The European Space Agency has already flagged Enceladus as one of its very highest priority destinations for a future flagship mission, with concepts on the table for a spacecraft that wouldn't just fly through the plumes like Cassini did, but would actually land in the south polar region and sample the material directly off the surface. NASA, meanwhile, currently has its Europa Clipper spacecraft en route to Jupiter's icy moon Europa, another leading ocean world candidate using exploration strategies built directly on lessons learned at Saturn. Astrobiologists now talk routinely about an entire category of places called ocean worlds, moons hiding liquid water under an icy shell, as serious, prioritized targets in the search for life beyond Earth. Enceladus, Europa, Ganymede, Titan, and now Mimas. 5 worlds in our own solar system, potentially hiding liquid water right now, this year, as you're watching this. Before Cassini, most of that list didn't exist. We had guesses, hunches, maybe 1 or 2 candidates on the fringes of serious discussion. After Cassini, we have hard evidence, chemical data, gravitational measurements, actual samples flown directly through actual plumes. And the papers still coming out in 2025 and into 2026 aren't closing that file. They're opening new ones. So think about what actually just happened here. A machine we built by hand, launched almost 30 years ago, flown for 2 decades, and then deliberately steered to its own destruction, is still handing scientists some of the most important discoveries of their careers, years after it stopped existing. Its final images, the ones the world watched, with a kind of sad ceremonial reverence back in September 2017, weren't the end of the story at all. They were a locked box. And it has taken almost a decade of patient, unglamorous work, researchers rerunning old numbers through new models, reanalyzing archived spectra with instruments and software Cassini's own engineers never had access to finally start cracking that box open. What's inside keeps turning out to be more extraordinary than anyone predicted back when the spacecraft was still alive. Organic molecules that mirror the chemistry of living cells, sprayed from a hidden ocean nearly 1 billion miles from the sun, a moon that looked like a dead rock quietly growing a brand new ocean in the last few million years, rings that are, on a cosmic clock, already disappearing, a magnetic field defying the physics we thought was settled. We sent a machine to the edge of the solar system to look, and it came back with some of the strongest evidence we've ever had that the conditions for life might not be unique to Earth at all, that they might be sitting quietly right now under the ice of a small, overlooked moon in our own cosmic backyard. Cassini's final images didn't close the book on Saturn. They opened a chapter we're still only beginning to read, one archived data file at a time.